Now we're recording, so no more talk of none of that. Cody, did you sign in? You did. All right. Anybody not sign in? Six. Nope, we're good. We were talking about current last time, electrical current, and pardon me while I clean up after the statistics guy. We got current is defined as, well, it's flow of charge. It's steady state moving electrical charge. 1 amp of current is defined as 1 coulomb per second, meaning 1 coulomb of charge moving past the cross-section, a particular point, a cross-sectional point in a wire every second. That is the definition of 1 amp. And since 1 electron carries 1.6022 times 10 to the minus 19 coulombs of charge for each electron, the reciprocal of that is 6.24 times 10 to the power of 18, which is the number of electrons that have to flow past a point in a wire every second in order to constitute 1 amp of current. And that, I think, is pretty much where we left off. Am I forgetting something? Okay, we talked about the battery. Well, I take it everybody here is already familiar with Ohm's law. I is equal to E over R. I is the current, stands for intensity. E stands for electromotive force. Most physics books now will write this as a script E for electromotive force, as opposed to the Latin E, because that tends to confuse people with the E field. And R in ohms. The symbol for ohms is the uppercase Greek letter omega. Y'all know how that works? The voltage pushes the current. How much current a given voltage pushes is inversely proportional to the resistance of the medium that it's pushing it through. The wire. How much resistance does the wire have, or the resistor, or the electrical load? Who can tell me the difference between series and parallel? This is going to a trick question, so everybody step up. What's the difference between series and parallel electrical circuits? Current going through. So, parallel and series. Same well, we're about to go through some more starting next week, I think. No, we're doing power, and then we'll get into ACs. But we are going to go through circuits. Parallel series circuits, Kirchhoff's voltage laws, solving systems of equations for complex circuits. Same current through each. Parallel, they get the same voltage. Across each. So, now here's the trick question. Is that battery and that resistor in series or in parallel? You got a battery and a resistor. Is this circuit series circuit or parallel circuit? It's series circuit. Why? Because you've got the same current flowing through here as flowing through there. But you've got the same voltage across the battery and across the resistor. Now, isn't that supposed to be the definition of parallel? You're getting dangerously close to the answer. Continue your thought. You're very close. You got the right idea. It's not a legitimate question to ask if this is a series or parallel circuit. Series and parallel can only describe the relationship between loads or between sources. You can't talk about the relationship of you can't talk about, in this case, you have a source and a load. So if you're going to talk about whether they're series or parallel, the closest thing you can come to is whoever it was that said they're both. Because they are, in fact, both in series and in parallel. But that's not a legitimate statement because they're not both the same thing. One's a source, the other's a load. A trick question. No, seriously, it's a trick question, but I ask it because I want to get people to thinking about this sort of thing. Until someone points out that it's actually also parallel, and then you'd start getting confused. Well, all right. I take it here, everyone can figure out how much current is flowing if you put a 1.5 volts across a 5 ohm resistor. Yeah, you're going to get 1/3 of an amp or 0.3 amps. And I'm sure everybody knows the color code for resistors. Do you all know the color code? There will be no recitation of the mnemonic in this class. No, you can write down the color code if you want to, but I've heard the mnemonic that most electronics classes teach for memorizing the color code. You weren't? Oh, you ain't going to get taught that one from me. Well, actually, nowadays they have actually started where they now that everything's going surface mount, they really have started getting away from the color codes. They've come up with other methods of denoting things, namely with digits, with actual numbers. But even then, you've got to know what they mean. You talk about an 805 chip resistor. You've got to know that that's 80 thousandths long by 50 thousandths wide. Anyway, let's move on to 18.4, resistivity. The wire that current is flowing through has some resistance. Now, if it's a good conductor, it doesn't have very much, but it's got some. We used a wire with high resistivity in our Wheatstone bridge yesterday in lab. Now the resistance of that wire is going to be proportional. Yeah, let me change that to proportional. The resistance of the wire is proportional to its length, meaning that the longer you make the wire, the bigger the length, the bigger the resistance. As the length increases, so does the resistance. And it is inversely proportional to its cross-sectional area. The area, if you cut the wire in half, what would the area of the circle of its cross-section, how much area would it be? The bigger it gets, the smaller the resistance, the more the resistance goes down. So you take a wire, you make it larger in diameter, resistance goes down. You make it longer, resistance goes up. This becomes an equality when you multiply it by a coefficient, rho, or resistivity. Who here can tell me what a mho is? And it's spelled M-H-O. This is not part of the text, but just for your own edification, mho is the unit of conductivity. Conductivity is the reciprocal of resistance. So if resistance is measured in ohms, mhos, which is just ohm spelled backwards, are 1 over ohms. Yeah, that's where they got it from. I was just thinking about how back in the day we didn't just learn about resistivity and resistance, we also had to learn about conductivity and all the inter-reciprocal relationships and stuff. Look at this equation. Who can tell me the units of resistivity? Ohm meters, exactly. Ohm meters. When you multiply ohm meters times meters divided by meters squared, you're left with ohms, which is your resistance. Table 18.1 lists a bunch of conductors and semiconductors and insulators and gives their various resistivities. For example, silver has the lowest resistivity of all at 1.59 times 10 to the minus 8 ohm meters. And that is why they call the little instrument you use a multimeter or multimeter, because ohm meter is something else. That's just a joke. Y'all feel free to laugh anytime, okay? How many of you knew that silver was the best conductor we have? Copper is actually the second best conductor. It's cheaper than silver. It would get real expensive to wire your house in silver. Okay. I got to tell you, you know what? I've seen stupider things done. Have you ever seen someone put gold faucets in their bathrooms? That's just stupid. I mean, I don't care how rich you are. That's just. Conduct as contact points. Now, do you know why? No, there is a reason, and it's because gold does not corrode. That's why in the space program they make these satellites and these probes that have to fly through the deep freeze vacuum of space for decades before they get where they're going. And then once they get there, something's going to happen and a relay contact is going to close and everything has to happen at that point after it's spent 20 years floating adrift in, 200 degrees below zero temperature. It gets one chance to work, and only one. It's got to work that time. You don't put copper that can oxidize and corrode and build up a layer of, literally a layer of dielectric. Probabilities. They do. It's all based on probabilities, and they try to give it the highest probability of success that they can. That's why your airbags in your car, even more so in a car than in a space probe, the airbag in your car has to have gold contacts, because hopefully it's going to sit there for its entire existence and never once do anything. But in that microsecond when it needs to work right that time, every time. So they use gold contacts. So doesn't matter how long you leave it sitting out in the yard getting rained on and freezing and thawing, it's not going to corrode, it's not going to. That's why you use gold for contact points, but even then you don't use pure gold. You use gold plated on top of nickel, because nickel is hard and it won't deform. You just use solid gold. It's soft, it's going to get all mushed up every time. Mm-hmm. Oh yeah, I would definitely want to know this information. Let's use this table in a couple of examples here. Speaker wires. Suppose you want to connect your stereo to remote speakers. Each wire must be 20 meters long. What diameter copper wire should you use to keep the resistance less than 0.1 ohms per wire? I want to make sure that's not mine. Mine's close enough. Unless one of you's driving a truck, it ain't you either. Okay, this is basically the problem. You got a wire that's 20 meters long. how, and it's going to be made of what? Copper. So you got a copper wire 20 meters long. What diameter would you have to make it in order for it to only have 0.1 ohms of resistance? So we've got 0.1 ohms. What's the resistivity of copper? .68 times 10 to the minus 8 ohm meters. Remember your units. Times 20 meters. Was it 20 meters? 20 meters divided by area, A. So, let's just rearrange this algebraically. If anyone has, everyone want, tell me if I'm losing anyone here. I'm going to multiply both sides by A and divide both sides by 0.1 ohms. Now, let's check our units. I've got ohms divided by ohms, leaving me with meters squared and area, which will be in meters squared. So the units are good. What is the area of this 20 meter long piece of copper wire? .36 times 10 to the minus 6 square meters. I put a -6. It did come out looking like a 2, though, didn't it? Okay. Now, that means pi times r squared is equal to 3.36 times 10 to the minus 6. 7 meters squared. If I divide both sides by pi, r squared is equal to what? Gesundheit. Now just divide the 3.36 times 10 to the minus 6 by pi, and we get -7 or 6? -6. Meters squared. And if we take the square root of that, .03 times 10 to the minus 3 meters. And double that to get the diameter. We end up with 2.06 times 10 to the minus 3 is our diameter of copper wire that we need. Or basically 2 millimeters thick. Now let's go and put into use some of that Ohm's law that we have, that we all know how to use. How much voltage drop are we going to lose on that 20 meters of wire if we're running 4 amps through it? E equals I over R equals 4.0 amps divided by 0.1 ohms. Wait, that's not right. I equals E over R. I got it wrong. It's I times R, not I divided by R. Equals 0.4 volts, exactly. So, let's go. This is it. What time we got? Yeah, this is it. All right. And this is in your homework set. This should be in your homework assignment. One of your homework assignments is a problem dealing with this very thing. We're going to look at the temperature dependence of resistivity. So let me clear out some space here. What, did I erase something before you got to? Did I erase something too quick? Oh. Yeah, I have. All right. If you look at table 18.1, you'll notice the far right column gives a list of temperature coefficients of alpha. And alpha has units of degrees C, or 1 over degrees C. Now, you will also notice in the very top line of the table that it specifies that these resistivity and temperature coefficients are specified at 20 degrees C, which is basically room temperature. Okay? What if we were going to operate that copper wire at 40 degrees C? So you're building it to go in the hood of a car, under the hood of a car, where it's not going to be working at room temperature. It's going to be working at, say, 40 degrees C or 50 degrees C. What is then the resistivity at that temperature? Here we have let me make sure I write this correctly. 1 plus alpha times there we go. Okay, what is T? T sub naught and rho sub naught are the temperature at which the nominal value is defined for. In the case of table 18.1, T sub naught is 20 degrees C. And rho sub naught is whatever is listed there in the table. It's the resistivity at T sub naught at 20 degrees C. So T minus T sub naught is the change in temperature that you're going to actually operate at. It's how many degrees away from nominal are you going to be operating this piece of wire in this case. Okay. For every degree of change, or for every degree of delta T that you operate at, you're going to adjust your resistivity coefficient, rho sub naught, by that many degrees C, by that much per degree C. Let's just plug in the numbers and see how this works. We were talking about a copper wire, so rho sub naught for copper was how much? Okay, that's our rho sub naught. That's at 20 degrees C. Now what is the coefficient, the temperature coefficient alpha for copper? Okay, 6.8 times 10 to the minus 3. One over degrees C. Times, we're going to be operating at, what did we say, 50 degrees C? Minus 20 degrees C. Okay, what's 50 minus 20? 30 degrees C. So we're going to be moving 30 degrees. Those cancel. What's 30 times 6.8 times 10 to the minus 3? What one? I haven't added it yet. I'm working my way back. What's this? 0.204. You'll notice that it is now unitless. The degrees C cancel out with the 1 over degrees C. So it's just 0.204 added to 1. We will multiply by our 1.68 times 10 to the, what, minus 8 ohm meters. So what is 1.68 times 10 to the minus 8 ohm meters times 1.204? You'll notice because we included the 1 that you were asking about, we're keeping the initial value that we start with, and we're adding to it 0.204 more. That is this. That is our new resistivity at 50 degrees C for copper. So, I just made it up. I said we're going to be operating, instead of operating at 20 degrees C, which is what it's defined for, we're going to be operating it at this higher temperature. What if we were operating it at a lower temperature? What if we were going to build this to operate on a wind turbine at an Antarctic laboratory station somewhere? Then it would, yeah, it would decrease. Well, what it would do is it would, this many degrees, it changes. See, if this is 0, if we are just operating at T naught, this is T naught minus T naught is 0, which makes this 0, which makes this whole bracket just a 1. So our rho at 0 is going to be equal rho at 0, rho at 20 degrees. Here we go to a higher temperature, we subtract that 20 degrees, and we're left with a positive number. that multiplies this number of degrees C for each one of this much more resistivity for every one of those extra degrees C we go up. But if this number were less than 20 degrees C, then this would become negative, and for every one of those changes in temperature of degree C, we would change the coefficient of resistivity by this much, but then it would be subtracted from 1. So we would be multiplying by a number less than 1, and this value would be less than this. This value would go down. Yeah. No. Sometimes it'll be 20 degrees Celsius. Sometimes it'll be 0 degrees Celsius. Sometimes it'll be 25 degrees Celsius. But it will always be specified in your data. Exactly. Exactly. This is the temperature you're going to operate at. This is the temperature that rho sub naught is specified at. Well, you're either going to add or subtract depending on whether this difference, this is your delta T. If delta T goes up, you could. No, what do you mean PT? Oh, a negative here? No, not without getting into superconductivity. And we're not going there. No. This is your coefficient from the table here. This is how much this changes for every degree C that you go up or down. This will go up or down that much for every degree C that you move in operating temperature. You go up, your delta T is positive because it's a larger number minus that. If your operating temperature goes down, if you're going to operate at a lower temperature, then this minus T naught becomes a negative number. This negative number multiplies by alpha, that much change per degree C, subtracted from 1. Yeah. But what you're asking is, could this term ever equal -1? And that would happen if T minus T naught were equal to -1 over alpha. If that equaled -1 over alpha, then this would become alpha times -1 over alpha, which would be -1. And 1 minus 1 would go to 0, and your resistivity would go to 0. And at that point, it would take 0 voltage to push infinite current. Okay? Which doesn't make a lot of sense. In point of fact, there's a whole field of study in superconductivity, but you have to get into a whole bunch of exotic physics and things that happen at the molecular level before you start dealing with any of that. Nothing we ever do. You got to get down to liquid helium temperatures, which is like 4 degrees Kelvin. 4 degrees above absolute 0 before you start seeing these you got to at least get down to like liquid nitrogen temperatures to start seeing superconductivity effects. Yeah, it would be. Anything you find on the test is going to use. Yeah. So anyway, we did this, and we found that rho at 50 degrees, the resistivity of that copper wire at 50 degrees C is going to be 2.02 times 10 to the minus 8 ohm meters, not 1.68. That's a significant change. That's going to change the value of that 0.1 ohms. It's not going to be 0.1 ohms anymore. It's going to be, what, more than 0.1, more or less? More. But do we have to go back and redo that whole calculation where, okay, what was the diameter and the area and the length and all that? What if we were just asking, what was the resistance of that wire? No, the resistance of the wire that we, 0.1 ohms, right? That was equal to 0.1 ohms, which was equal to the resistivity at 20 degrees C, rho sub naught, times the length over the area. We could change rho sub naught to rho sub t if we multiply rho sub naught times this. Okay? I can get there a lot simpler than that. Rho at temperature is going to be equal to rho sub naught times 1 plus alpha times t minus t sub naught. Boom. Right? What if I multiply this times length over area? And this becomes resistance at temperature, which is equal to, this is the rho sub naught times L over A, is the resistance at 20 degrees C. So, all I'm pointing out to you is that you could work this problem if you were just given the resistance of a wire or a conductor of some kind at temperature instead of the resistivity. If you're given the resistance, you can find out how much the resistance is going to change by doing this directly, applying this directly to the resistance and get the new resistance. You don't have to go through the whole calculate the calculate the area and the length and do all of that to come up with, to convert resistivity into resistance. And then, you see what I'm saying? I think there's an example of this in the book. Right here. Example 18.7. Resistance thermometer. The variation in electrical resistance with temperature can be used to make precise temperature measurements. Platinum is commonly used since it is relatively free from corrosive effects and has a high melting point. Suppose at 20 degrees C, the resistance of a platinum resistance thermometer is 164.2 ohms. Notice we haven't talked about the resistivity of platinum at all. When placed in a particular solution, the resistance goes up to 187.4 ohms. What is the temperature of that solution? Well, oh look, they do the same derivation I just did, where you just multiply by L over A. Right here. Let me clear out some board space here. We're going to do this. What's the resistance? What's the resistance go up to? Once it's in solution, it goes up to 187.4 ohms. That then is equal to, what's it start off at? At 20 degrees C. Times 1 plus alpha T minus T sub naught. So that's 164.2 ohms times 1 plus, what's the coefficient, what's the temperature coefficient of platinum? .927 times 10 to the minus 3. Cody, 10 to the minus 3. Okay. Times T minus, what's T sub naught? No, T sub naught. 20 degrees C. So, how do we solve this? Let's first divide both sides by 164.2. So what's 187.4 divided by 164.2? Yeah, divide 187.4. Say again. 1.14. Is that really all the... Okay, well, we've got 4 digits here, so I'm going to keep the 4th digit. .141. Okay. And that's equal to 1 plus 3.927 times 10 to the minus 3 all right. We subtract 1 from both sides. Don't need a calculator to do that. 0.141 equals 3.927 times 10 to the minus 3. Let's go back to our units here. That's right. This is ohm. No, this is per degree C. This is 1 over degree C. Times T minus 20 degrees C. We divide by this per degree C. When we divide by 1 over C, we get degrees C. So what's 0.141 divided by 0.3927 times 10 to the minus 3? Yeah. .91 degrees C, because we divide it by 1 over degrees C, which puts it back on the top, is equal to T minus 20 degrees C. We add 20 degrees to that, and we get basically, 55.91 degrees C. How close are we to the book? They said 56.0. To 3 digits. No. No. And I don't know how many times we rounded before we came to our final answer. Yeah. Yeah. So, but the point is, every time you round something off and then keep using it, you've added a little bit more error. Okay. There you go. And look at that. Our time is up. If anyone has any, before y'all leave, does anyone have any homework questions? All right. What questions do you have? You bet. You certainly can, or you can also come in on Tuesday and make it up then if you can. That's more convenient. Doesn't matter.